What's up everyone, Mandar Chakrabarti here. Hope you all are doing great. In the last couple of videos, we have been going through the concepts of vector analysis. And why have we been going through all of that? Because electromagnetic field theory relies heavily on vector analysis. In today's video, we want to continue on in that trend and we will dive a little bit deeper into your vector analysis. And today we get introduced to the del operator, and we are starting right now. Okay, so a little bit of recapitulation time. Remember back to the first video when I told you that these four equations are the secret behind the entire world of wireless systems, that these four equations are the fundamental of the entire electromagnetic field theory? Well, if you look at all these four equations, one thing that you will find very common amongst them is this little inverted triangle over here. So what on earth is this inverted triangle? Let's figure that one out, shall we? Okay, so let's get started. Now, this little inverted triangle, that one is known as the vector differential operator. So the vector differential operator or del operator, it is basically a Greek symbol. In the Greek symbol, it's known as the nabla. The vector differential operator is essentially, it is used in the vector calculus and it determines how much a vector changes in each of the three primary directions. Didn't really understand? Well, let me try to again help you visualize the concept. Visualization is key in this particular subject. So consider that these are your three primary directions. So you have your x-axis, you have your y-axis pointing towards you, and you have the z-axis which is pointing upwards. So this is a vector. This is a three-dimensional vector. So this three-dimensional vector has got components in the x-axis, in the y-axis, as well as in the z-axis. So this three-dimensional vector, as it is moving along in space in this direction, remember vectors have a direction and we are dealing with movement for a vector. So as this vector is moving along this direction, this vector must be changing in value with respect to this axis, it must be changing with value with respect to this axis, and it must be changing in value with respect to this axis. So just how much these changes are, that is what this inverted triangle or this vector differential operator tells us. That is what it is all about. So it is essentially the partial derivative of the vector function in the three primary directions. Mathematically, the del operator is represented by this formula. But there is a lot of intuition that goes behind just this formula. So let's try and understand some of that intuition. So, before actually diving into your vector differential operator, let me take you a few steps back. Let me take you back to school, and this portion should be a little bit scary. At least it is for me. How many of you actually remember each and every one of these? I certainly don't. Or how about these? Or how about these? Do you actually remember each and every single one of these? I don't. Well, these were the differentiation tables, right? And we have learned them and we have basically memorized them. But we have also learned how these actually come about, how these are actually derived from a graphical point of view. And the reason why I say from a graphical point of view is because when we are going to be dealing with the vector situation, we actually need to derive these from a graphical point of view. When we deal with vectors, we are not going to have such very standardized expressions like these over here. So in that case, for that specific expression, if we want to calculate the differentiation, we must be able to do it graphically. So let me help you remember with one of the very simple examples. I'm pretty sure that every one of you are familiar with this particular figure. This one is a parabola. And what's the mathematical expression for this? Mathematically, it is expressed by y is equals to x squared. So if I want to calculate the differential of this, then essentially I'm trying to calculate dy dx. So dy dx in this particular case is ddx of x squared. Now you are going to tell me, why am I wasting your time? This one is so very simple. You already know the answer. The answer is 2x, right? But how did that answer 2x come about? You know the answer because you have it memorized over here. But how did this 2x answer come about? Let's look at it at least graphically. So when we are dealing with this sort of a parabolic expression, y is equals to x squared, right? So if I take a point x is equals to 2 on this graph, then y is going to be 4, of course. If I were to take a point x is equals to 3 on this point, y is going to be 9. Of course, this is going to go beyond the scope of this particular graph. Anyway, so the way that we approach the differentiation is again by considering two similar points like these. So what we do is, I'm just going to show it to you over here. So I'm going to start off with one point. Let's say I take this particular point and I'll bring that down to my axis over here, and I name that point as say x1. And I will take another point over here and I'll bring that one down also to the axis over here. This one I name as x1 plus h. Okay. And the thing is that h tends to 0. So essentially these 2 points are very close to each other. Now in this particular figure it may not appear that these 2 points are very close to each other, but you can consider it that we are zooming into the figure over here to check out what's happening. Okay, so let me find out the corresponding y-axis terms over here and over here. Let me name them. So this one I name as y1, this one I name as y2, and I'll give them a couple of different names as well. So this one I call as f of x1, and this one I call as f of x1 plus h. Okay, you'll see why I did that in a couple of seconds. And essentially, if I want to calculate dy dx, then the only thing that I'm actually trying to calculate is y2 minus y1 divided by x2 minus x1. That is the only thing. This is the only thing that we are trying to calculate. So in our particular case, this becomes your dy dx becomes y2, which is f of x plus h. So f of x plus h minus f of x, x1 and x1, let me stick to the name that I've given, divided by x1 plus h minus x1. Okay, so outright x1 cancels out and I'm left with f of x1 plus h minus f of x by h. With one consideration, limit h tends to 0. This is dy dx. Okay, I need a fresh page to work. Right, so inputting our specific expression over here, till now we have got dy dx is equals to limit h tends to 0 of f of x1 plus h minus f of x1 divided by h. Right? Go back, check it. There you go. Alright, so f of x1 plus h, the original expression was y is equals to x square. So f of x1 plus h is basically going to be x1 plus h whole square. So that means limit h tends to 0, x plus h whole square minus x square divided by h. So that means limit h tends to 0, x square h square twice xh minus x square divided by h. Am I doing everything correctly? Yeah, seems right. Okay, so do a couple of terms cancel out? Yes, they do. This one cancels out with this one. And h square. So if h tends to 0, if h is a very small value, then h square is almost insignificant. So if I say it's almost insignificant, that means that h square can also be considered as 0. Finally, what I land up with is limit h tends to 0, this is 0 already considered, twice xh by h. Surprise, surprise, this cancels out and I am left with twice x. My, doesn't this seem familiar? So, dy dx is equals to twice x. How did we arrive at this? By considering originally 2 points. So, I have considered one point here, another very close point on the curve, and by considering the difference between these two results. So, this one and this one. And these are the exact same steps that we are going to be requiring when we go into calculation of the vector differential operator. Okay, now we have stated that the vector differential operator is the partial differential operator in all three directions. So just a very quick recapitulation of partial differential operator. So the partial differential operator or the partial derivative is derivative with respect to only one of the variables when the other variables are kept constant. So if I were to give you a specific equation, something like this one. So if I give you an expression something like this, can you calculate and tell me what would be the partial derivative with respect to x of this particular value? Can you do that? Okay, let me just show you the answer. So partial derivative with respect to x is going to be this. Whenever we have x, we differentiate for it, the other two terms are kept as constant. So based on that, now why don't you tell me partial derivative with respect to y? Go ahead, make the calculation, pause the video, make the calculation, and say the answer. Okay, so if you have got that, then the answer should be something like this. Next, calculated partial derivative with respect to z. Okay, so if you have calculated partial derivative with respect to z, then you should have got an answer something like this. Alright, so this is your partial derivatives. Now, just for fun, what if I were to take these three results? So you have 1, 2, and 3. So what if I were to take these three results and all three of them together in a form something like this. This one that we got in a vectorial form. Just for fun, I have thrown in a little vector inside as well. This that we get is known as the gradient operation. And essentially, it is the slope of this particular function. Okay, now that I have primed you a little bit, in the next video, we are going to go into a little bit more calculations, and just as we calculated the derivative for this one, in the same way now we take this and make this one into a two-dimensional curve, which is something of this sort. So in the next video, I want to have a discussion with all of you on how to calculate this one. Okay, so that's it for this one, and I'll see you in the next video. So, alright, take care. See you soon.